This is video 8 for chapter 20 on electrolytic cells. After you've watched this video, you should be able to compare and contrast an electrolytic cell to a voltaic cell that you learned about earlier. So this video should just give you some of the overview of an electrolytic cell, and then we will spend more time in class doing some of the math and some more detailed explanation of electrolytic cells. So a voltaic cell we've learned about already, and in a voltaic cell we know that they use a spontaneous redox reaction to produce electrical charge. So a voltaic cell utilizes what a spontaneous reaction would be, so something that happens kind of naturally. You know, if you put a copper wire in silver nitrate solution, you are going to get a reaction. So copper solid plus silver ion could definitely be used as a voltaic cell. In an electrolytic cell, you're going to use a reaction that would normally be non-spontaneous, and you're going to force that reaction to happen by using an external source of voltage, so like a battery or something to power this reaction. You guys actually have seen one of these back in your first year of chemistry. If you think back to Ms. Kaufman's class, you did an experiment called types of reactions, and one of the reactions she did as a demonstration for you, she used something called the Hoffman apparatus, and in it she put some water, and she ran electricity through the water to generate hydrogen gas and oxygen gas. So we know that water does not normally decompose into hydrogen and oxygen on its own. We have to force that to happen by using a power source to get the water to break up. And so we did that for you as a demonstration using the power source that we have in our demonstration tables. You might remember that, and if not, we can talk more about that in class, but that is an example of an electrolysis reaction or an electrolytic cell. Now, the reason we use electrolytic cells is because this is how we can get some elements to be generated that are not normally found in nature. For example, both sodium and chlorine are important elements, but they do not exist by themselves in nature. You can't mine for sodium metal the way you can mine for iron. What we can find, though, is salt, NaCl. So if we can get salt and use electrolysis to split it into pure sodium and pure chlorine, then we can actually get those elements to use for what we need them, you know, in industry. So this is a process that's used often in industry. Again, another example of this would be aluminum. Pure aluminum metal is used in lots of products that you guys see every day, pop cans just being one of them. Now, aluminum metal doesn't exist very often in nature by itself, but the oxides of aluminum do. And so if we can use aluminum oxide and run electricity through it to produce aluminum and oxygen, then we have our pure aluminum that we need for manufacturing. So that's why we use electrolytic cells. That's why we would want to take electricity and make a reaction split into something that normally would not happen on its own. Now, an electrolytic cell has some different parts than the voltaic cells would have. So first of all, an electrolytic cell has to have a source of electric power. You need something to get what naturally would not happen to happen. You need an electrolyte, and that will undergo some kind of a chemical change when you're doing this process. Usually we use a molten salt or an aqueous solution of an ionic compound, and we're going to talk about those a little bit more in the next few days. You need electrodes, which are either made from some metal or from graphite, and if you don't know what graphite is, it's a form of carbon. And those metals are connected to the power source, and it's very important that they don't touch each other when you're doing the reaction. And then lastly, you need some electrical wires so we can get the electrodes to the battery or the power supply that we're using. Now, these are important things to remember. In both voltaic and electrolytic cells, oxidation always occurs at the anode. Reduction always occurs at the cathode, okay? So that will be true. They compare that way. Oxidation always occurs at the anode, reduction always occurs at the cathode, regardless of the type of cell you have. But or also in both kinds of cells, electrons always flow from anode to cathode. So I'm going to do this. And you may want to add this into your notes if you have room for it. If we think of a voltaic cell, since a voltaic cell happens naturally, the anode, I think I've drawn this for you before. Think of the anode to the cathode like a hill. Okay? Now we know that the anode is negatively charged in a voltaic cell and the cathode is positively charged in the voltaic cell. And it's a natural process for the electrons to be generated at the negative, and they will naturally be attracted to the positive cathode. So think of that as running down the hill, and this happens spontaneously. Okay? Now, in an electrolytic cell, we're forcing this reaction to happen. So I'm going to just give you a different diagram here. In an electrolytic cell, what has changed is where the cathode and anode are placed in relation to, if we think of our analogy of a hill. Okay? Now, we're forcing electrons, we're forcing them to go from the anode to the cathode. In an electrolytic cell, the anode is positive and the cathode is negative. That's what's being forced to happen. We are forcing electrons to go up this hill by using a battery or some other power source. So they're forced. So they are forced to go to the electrode they don't normally want to. Electrons are being forced to go to a negative electrode. Okay? So in a voltaic cell and in an electrolytic cell, electrons always flow from anode to cathode. Anode is always where oxidation happens. Cathode is always where reduction happens. That's where they are similar. The difference is that in a voltaic cell, the reaction is spontaneous. The electrons naturally flow from the anode to the cathode. But in the electrolytic cell, we are forcing them to do this using a battery or some other power source. And so that is a non-spontaneous process. So on this last little slide, we are comparing and contrasting the voltaic cell to the electrolytic cell. So whereas a voltaic cell is a spontaneous redox reaction that produces electricity, our electrolytic cell is non-spontaneous, and we are using electricity to make that happen. In a voltaic cell, we are taking what a normal chemical reaction would do and converting that chemical energy to electric energy. But in an electrolytic cell, we're doing the opposite. We are taking electric energy and converting it into chemical energy to get the elements that we desire. So like pure sodium, pure aluminum, like I mentioned earlier. In a voltaic cell, the anode is negative and the cathode is positive, and in the electrolytic cell, that switches. So the anode is positive and the cathode is negative. I really do think that the hill analogy will help you. If you can think of, in a voltaic cell, the hill happens naturally. In the electrolytic cell, still goes from anode to cathode, but you have to switch them. You have to push those electrons up the hill. Now, when you come to class tomorrow, we will watch the most exciting video ever made on electrolysis. So look forward to that.